Hello everyone, my name is Edward Becker and I'm a faculty member in the School of Architecture and Design at Virginia Tech. I'll be presenting today jointly with Kevin Lee, co-author of our article and an architectural designer at Studio MB in Washington, DC, formerly a project designer at Kaiser Path. Today we'll provide an overview of our case study research on Carbon12 in the Canyons, two mass timber projects designed and developed by Kaiser Path in Portland. I'll provide an introduction to our research, followed by detailed case study information from Kevin, and then I'll complete the presentation with a few discussion points and some conclusions from our research. It's worth noting that while Europe has led the way in terms of mass timber construction for decades, a significant amount of urban growth and construction globally is projected to occur in countries with limited mass timber experience and limited mass timber industries, much like the United States. That said, our case study research is intended to provide a roadmap for mass timber projects globally in non-European contexts that likely will face many of the same challenges as Carbon12 and the Canyons, namely outdated building regulations and a perception that mass timber use is unsafe, among other concerns. Our research relating to the two case study projects, Carbon12 being one, shown on the screen, specifically focuses on the integrated workflows that allow project teams to effectively coordinate nearly every aspect of the design to construction process, thus leading to faster, lower cost, and lower carbon construction outcomes. The work postulates that data-driven design solutions that prioritize fast and efficient construction with low carbon materials like CLT may provide a solution for the AEC industries over the coming decades, particularly as they attempt to overcome the inverse or wicked challenge of rising urban populations on one hand, with the need to lower greenhouse gas emissions on the other. As evidenced by the European Commission in the United Nations reports, the world's urban population is expected to nearly double by year 2050 from the 4.2 billion people in cities today. Construction spending alone is expected to cost from 9 to 11 trillion US dollars to support urban population growth globally and a related provision of adequate housing in cities by 2025. While the baseline demand for new housing units over the next decade is forecasted to be 16 to 18 million units in the US alone, globally up to 90% of the aforementioned 11 trillion US dollars is expected to be spent in Asia and Africa. How can such housing be constructed in an efficient way, as we can ask when looking at the image on the screen? Yes, it certainly can be, but the question really is architecturally, how do we make it meaningful and how do we do it in a low carbon manner? The Brock Commons project in Canada, shown here, is an excellent example. Inverse to the increase in housing units needed globally is also the need to lower carbon emissions, particularly embodied carbon. Operational carbon can be lowered very effectively and quickly as new technologies develop, but embodied carbon is there to stay, so we have to address it on the front end. In the US, as in other appropriate locations for wood construction globally, outdated building codes are catching up, but key obstacles remain for the widespread adoption of mass timber construction. So as Kevin will talk about related to the two case study projects, information transfer, integrated project teams, and early collaboration are really key to overcome these contextual hurdles moving forward.
Thanks, Edward. So the physical context of both projects is that they're located in Portland, Oregon, in the Pacific Northwest area of the United States. And it's significant to note that mass timber in North America actually developed in Canada up north and then came down south to the Pacific Northwest of the United States. And this building technology gained momentum in the city of Portland specifically because the city historically had a thriving timber industry, was familiar with heavy timber construction, and is currently a rapidly growing city searching for housing solutions. So in the context of time, Carbon12's origins, which we'll elaborate on a little bit later, occurred prior to the new Type 4 IBC code changes. Therefore, it's pretty important to note that the team's ability to overcome code hurdles literally paved the path for not only other Oregon mass timber buildings, but also propelled Carbon-12 to become a basis for the new Type 4C construction type. And in the following paradigm shifts on the right, the Canyons project proceeded in a supportive environment with not only jurisdictional familiarity and clear code paths, but also increasing consumer demand. So what is Carbon-12? Carbon-12 is an 8-story multifamily building located on a tight urban site. It features 14 premium condo units above a ground floor commercial space. And as you can see in the plan to your right, each floor plate contains 2 units wrapped around the central core containing a personal egress stair, as well as a central elevator that opens directly into each unit. And structurally, it has a hybrid system of exposed cross-laminated floor panels supported on glulam columns and beams, which are tied back to that steel core housing the elevator and stairs. And so after Carbon-12, Kaiser Path developed and designed the Canyons, which is a multifamily mixed-use building located directly to the south of Carbon-12, which you can see in the upper left photo. Canyons is both the 6-story building as well as the strip of 2-story retail units you can slightly see on the right. But for the purposes of our paper, we focused on the main building, which contains a double-loaded open-air atrium housing the 70 market rate residential units. And structurally in the main building, a different hybrid system of exposed CLT floor panels were placed on top of light frame wood bearing walls. And so as we transition into reviewing the key takeaways, it's pretty important to understand the composition of Kaiser Path. So as you can see here, Kaiser Path is composed of an architectural firm, Path Architecture, and a developer builder company, Kaiser Group, Inc. As you can see, the immediate team is quite small, but having the developer, builder, and architect all in-house means maximum communication, control, and flexibility between the major parties. And this ability to efficiently make decisions immediately in-house benefited Carbon-12 from the very beginning all the way through construction completion. And if you were able to catch on the timeline slide, Carbon-12 was initially an entry for the Tallwell building competition in 2014 that was ultimately not selected. However, having ownership of the land as well as the consensus and determination of the project team gave Kaiser Path the ability to immediately decide to build Carbon-12 anyways. So through Carbon-12 and eventually the Canyons, a key goal throughout was to facilitate process efficiency through close communication during both the design and construction phase. So during Carbon-12, as we mentioned, the majority of the project team was in-house. The decision then was made to engage the timber manufacturer, Structurlam, and the subcontractor responsible for both steel and timber superstructure early in the project. And due to the successful collaboration in Carbon-12, Structurlam and that same subcontractor group were again engaged for the Canyons project. However, it is good to note that in this case, the team actually reverted back to more traditional roles as an external general contractor was engaged to undertake the significantly larger project. So technologically, in Carbon-12's process, both the architect and the general contractor utilized the same Revit model as both parties were entirely in-house. In the Canyons, the architectural Revit model was shared with the external general contractor, who in turn adapted it to fit their needs. And in both cases, this architectural model was shared with Structurlam, who adapted it into their cohesive mass timber package. So a key takeaway overall is that an extensive pre-design and pre-construction coordination results in a streamlined assembly process. So the team's primary strategy, especially in Carbon-12, was to maximize the superstructure's construction speed to increase time-related savings, as well as to minimize exposure to what was a notoriously wet winter climate in the area. As CLT could not be utilized in the central core due to local seismic restrictions, mechanically fastened steel, also known as buckling restrained brace system, was chosen instead of concrete due to its erection speed compatibility with mass timber. And that you can see in the upper right photo. On the left, you can see an example of how the steel core was erected at 3-floor increments and then followed behind by the glulam structure and beams that are tied back to that steel superstructure. And the entire superstructure, including the CLT panels, took approximately 8 weeks. The team also coordinated with Timberland, which was the aforementioned framing contractor, with their internal steel divisions so that they could directly fabricate and install the steel core in conjunction with the timber package that they received from Structurlam, meaning that one sub was in control of the framing steel and wood. And early engagement with Structurlam as well also resulted in a uniquely pre-finished panel that was installed directly from arriving delivery trucks, as you can see in the upper right, therefore completely minimizing on-site costs and potential damage during what later became known as the wettest winter in the city's history. So learning from the concepts that led to Carbon12's success, the canyons was also designed with a CLT-based structure due to the team's desire to achieve a similarly streamlined construction process. However, the canyons actually utilize a hybrid system that used exposed CLT floor panels over light frame wood bearing walls, and that was placed on top of a single-story concrete podium. The original intent was to prefabricate these light frame wood walls, you can see in the bottom left, for rapid modular installation to match that mass timber's assembly speed as we had previously learned in Carbon12. However, this was ultimately changed to traditional on-site timber framing with the added consideration that they were going to pre-cut the studs for increased assembly time. And so finally, starting in the upper left and going clockwise, the canyon strategy was to install the CLT panel starting from the east side, go to the west side, and then chase after it with the light frame wood assembly. And so as the superstructure overall continued to grow vertically, various trades could immediately come in afterwards and begin working on the floors beneath. So despite the framing changes we mentioned earlier, the light frame walls average approximately 6 days per floor, and the CLT assembly average approximately 3 days per floor. And that is all due to the careful coordination of all the involved parties.
So in conclusion, and relative to the discussion points in our paper, we focused on 2 primary discussion points, which I want to highlight here during the presentation. 1, the opportunities for offsite fabrication and integration in projects such as these. And 2, the opportunities to enhance design cost modeling. Relative to the canyon's prefabricated wall assemblies, the construction speed challenges that the project team experienced may be mitigated through higher end workflows that pair BIM data with advanced robotic manufacturing. So technologies such as the ETH's robot-based fabrication methods of timber frame modules may be of particular utility here, for example, assuming that tooling costs and on-site assembly logistics are managed. Additionally, a further integration of cost and design models could be beneficial across the mass timber industry to help streamline the design to construction process, specifically after initial project bidding. US architectural offices have shown an interest in such streamlining through projects such as B2 by Shop in Brooklyn and the algorithmically controlled mass timber designs of Boston-based Generate, shown here on the screen. Their Model C project specifically being driven formally by an efficiency script specifically developed for mass timber buildings. So relative to Carbon12 and the canyons, we hope that integrated workflows and data management that underpin these buildings relative to the key global challenges that urban areas face will be better able to be solved through these particular discussions. So thank you for listening today, and we hope you enjoy the related paper.